Section 13.7 is on tangent planes and normal lines. We have already studied equations of planes and equations of lines in space, so this is an extension of that. You can represent the surfaces in space primarily by equations of the form z equals a function of x, y. In what we're going to be using later, it is more convenient if we can represent it as a capital F, which is a function of 3 variables, equals 0. That's an alternative to writing z equals something with x and y in it, is to write everything, the equation, so that x, y, and z, a function of x, y, and z equals 0. In order to do that, if you have an equation z equals something with an x and y in it, you're going to subtract z from both sides so that you get that capital F of x, y, and z function. Here's an example. Suppose we have a function given by f of x, y, z equals x squared plus y squared plus z squared minus 4. If we want to describe the level surface given by capital F of x, y, z equals 0. If we set this whole equation equal to 0, we can identify this as a surface. So if you set that equal to 0 and add 4 to both sides, you get the equation x squared plus y squared plus z squared is equal to 4. Again, you should recognize that as a sphere. Way back in chapter 11, we were exposed to the quadric surfaces, and one of them being the sphere. So this sphere has a radius of 2, and the center of the sphere is at the origin. Tangent plane and normal line to a surface. Normal lines are important in analyzing surfaces and solids. For example, consider the collision of 2 billiard balls. When a stationary ball, that's the red one, is struck at a point P on its surface, it moves along the line of impact determined by P, the point, and the center of the ball. The impact can occur in 2 ways. If the cue ball is moving along the line of impacts, here's the point P, and if you look at the center of the ball, if it hits right there, the line of impact is going to go straight through the center of the ball. It stops dead. The cue ball will stop dead and imparts all of the momentum to the stationary ball as shown. So that's going to shoot off that way. So the line of impact is going straight through the center of the ball, so it's going to continue in that direction. If the cue ball is not moving along the line of impact, it is deflected to one side or the other and retains part of its momentum. That part of the momentum that is transferred to the stationary ball occurs along the line of impact regardless of the direction of the cue ball, as shown. So the line of impact goes straight through the point where it meets through the center of the ball. So the ball, if it's hit at this point, go through the center, it's going to move out in this direction. Excuse me. So the ball, the cue ball, is then deflected in this way. This line of impact is called the normal line to the surface of the ball at the point P. That's our normal line. It's normal to the surface at that point. Now again, we're going to be working with planes, tangent planes, and normal vectors, normal lines. So I have this slide here so you can recall parametric equations for a line in space. In order to come up with the equations, you need 2 things. You need a point and you need a parallel vector. So you're going to be using the coordinates of the point as your x0, y0, z0, and the components of the parallel vector a, b, c in your parametric equations for a line. To find the equation of a plane, you also need 2 things. You need a point and you need a normal vector. You'll be using the coordinates of the point for your x0, y0, z0, and the components of the normal vector a, b, c as your coefficients. To find the tangent plane, a normal line to a surface, let's look at the following slide. In the process of finding the normal line to a surface, you are also able to find the tangent plane. Now to find the equation of a line, you need a point, P, and you need a parallel vector. And if you want to find the equation of a tangent plane, you need a point and a normal vector. So you can see the relationship between these two. If you can find one, you can find the other. So let's say S is a surface given by this capital F of xyz equals 0, and the point is a point on the surface, then the gradient of that capital F of xyz is normal to the surface at that point. So in the last section, we learned about gradients. We are going to be using gradients in this section to find the components of the normal vector to the surface. So here are some definitions for a tangent plane and a normal line. If f is differentiable, again, that's a capital F function of 3 variables equals to 0, and you have a point, then and if the gradient does not equal 0, we could say that the plane through P that is normal to the gradient is called the tangent plane to S at that point P. Now the line through P having the direction of the gradient is called the normal line to S at P. Again, recall the equation of a tangent plane. So the way we are going to find the components of that normal vector is to evaluate the gradient at the given point. In this example, we're finding an equation of a tangent plane. Find an equation of the tangent plane to the hyperboloid given by z squared minus 2x squared minus 2y equals 12 at the point 1, negative 1, 4. So you want to begin by writing the equation some capital F of xyz equals 0. So we do that by subtracting 12 from both sides. Now we want to find the gradient. The gradient of the function uses those partial derivatives. Find the gradient, take the partial derivative with respect to x. You treat x as a variable and everything else as a constant. That derivative is negative 4x. Take the partial derivative with respect to y, and that's going to be negative 4y. And the partial derivative with respect to z is 2z. So these are going to be your components of the normal vector. And that's also the components of your gradient vector. So if we evaluate those partial derivatives at the point 1, negative 1, 4, plug in 1 for x, negative 1 for y, and 4 for z, we find that the components of the gradient vector at that point are negative 4, 4, and 8. So we're going to use those as our coefficients and use the given point 1, negative 1, 4 in the equation. And then you can simplify that by distributing, and then you can combine those constants. And then notice here that you can, these all have a common factor of 4. You can divide everything by a negative 4 so that you get the equation of a plane. This plane is tangent to the surface at the given point. So we have a portion of the hyperboloid and the plane that is tangent to the hyperboloid at the given point. Okay, to find the equation of the tangent plane at a point on a surface where you're given z equals f of xy, you can define the function f by subtracting z from both sides. So you have a capital F of xyz equals f of xy minus z. Then S is given by the level surface of capital F of xyz equals 0 and the theorem 13.13, an equation of the tangent plane to S at the point can be found by this. You take the partial derivative of this with respect to x and y and z, and that partial derivative with respect to z is going to be a negative 1 when you write the equation in this manner.